Good evening, Moses, Nandakumar, Surya, Prasita. The meeting is supposed to start at 6 sharp, but I see that very few of you have joined. So we'll just wait for some more time in case other participants join, and then start. Thank you. Hello and good evening, everyone. So, good evening, Anuj, Surya, Moses, Nandkumar, Prashita, Priyanka, Venki, Vethi, and Sheikh Altaf. And thank you for tuning in to the live sessions for the course on Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. I work in the broad area of metal additive manufacturing. This course, as you know, is in its rerun and it is taught by Professor Sajan Kapil from the Indian Institute of Technology at Guwahati. So I am teaching this course, well, assisting in the teaching of this course because I also work in this broad field, but it'll really help me um, gauge user participation. If a few of you could unmute and tell me why you are why you have joined this course and what are your expectations or key takeaways that you hope to gain from this course. Please feel free to unmute and speak up. Moses, are you there? Could you please share why you have joined this course?
Yeah. Good evening. Am I audible?
Yes, you are. Please continue.
Yeah, I'm Moses. I'm working as an associate professor in Hindustan Institute of Technology, Tamil Nadu. Uh, Actually, I enrolled myself in an ASAT QAP program. I underwent 2 weeks offline program at IIT Palakkad in the area of 3D printing. So the participants were asked to undergo two courses related to 3D printing in NPTEL. So that is why I have enrolled in this NPTEL course.
Okay, Professor Moses, and welcome to the course. I hope to learn from your experiences as well. It is great to have you with us.
Thank you.
Yes. Anyone else volunteering to share their purpose here? Anuj, are you there? Could you please share why you have joined this course? Maybe not. Okay, never mind. So we'll start. Just allow me a minute to share my screen. So once again, welcome to the course on the fundamentals of additive manufacturing technologies. This is taught, as you are well aware, by Professor Sajan Kapil from IIT Guwahati. And I can say, being in an IIT and having taken courses on additive manufacturing or say similar fields in one of the top IITs, being IIT Bombay, I can still say with full confidence that this course is one of the most exhaustive, comprehensive, and perhaps uh, one of the most logically designed courses in the field of additive manufacturing, especially when it comes to understanding of the technologies and the macroscopic view of the process. It does not delve much into the, say, microstructural features or what happens inside the melt pool or such things, but then it is an introductory course, and in that it truly excels. The way we'll go about this course is we have about 12 weeks with us, and every week we'll try to recapitulate the contents that were covered for that week. So typically you have anywhere from 2 to 4 lectures every week. and you are expected to go through the lectures. However, past experience tells us that sometimes it is not possible for you. So we'll run through a quick recap of whatever course content was covered, and then we'll go over a few illustrative problems, both subjective and objective types. And the the purpose of these problems is to help you A, solve your assignments better, and B, prepare you for the course certification examination. So often you'll find that some questions are similar, but the data, of course, will be changed. And in some cases, the questions might be totally different from what are available in the assignments. Still, they will hopefully help you um, score better and improve your understanding of the course. Now, during the course of this video, during the course of the session, in fact, so I'll request that you remain muted, and in case you have a doubt, anyway, we'll be taking up doubts at the end. But still, in case you have a doubt midway, I request you to raise your hand, and then I'll ask you to unmute, and then we can discuss whatever your point is. And otherwise, please remain muted, as any say undesired noises might be disturbing and may disturb other participants. So I just picked a few market trends from public sources on additive manufacturing. And for students or others like teachers associated with this field, additive manufacturing has become quite the buzzword. And there are courses, people and students are researching into it, papers are being published left, right, and center. But why the sudden push? Why the upsurge? And what is this buzz about additive manufacturing? And is it only restricted to our educational institutions and labs? So here is a plot of the market size in billions of US dollars against a timeline. So currently we are somewhere here. 2024, it's projected that the total market cap of additive manufacturing is somewhere around $4.2 billion, but it's a rising graph. And around 2030, it is expected to reach a market cap of 11.45 US billion dollars. So quite the opportunity for us. And if we focus on Asia, we see that, I mean, of course, in the world, US alone has captured or cornered 36% of the market. The next biggest leader is Asia with 28%. And among the Asian countries, China with close to 50% and Japan with close to 30% are the market leaders when it comes to, say, the implementation or at least money that they're pouring into the R&D and technological development concerned to additive manufacturing. Mehboob Basha, do you have a question? Could you please unmute? Mehboob Basha, do you have a question? Okay, maybe not. In case you have a question, please raise your hand again. Let us continue. And we see that in this pie chart, India has a market share somewhere around 5%, but we are growing steadily and we are gaining foothold. And if we look at the industry-wise picture of the metal additive manufacturing market, we see that in 2021, it was, say, almost evenly distributed between healthcare, automotive, and maybe a slightly larger share of the pie in aerospace. And aerospace is in fact the most common application that you will hear when you're talking to someone working in the field of AM. It is the first word to come out of your mouth. Even if you ask me, so what is the application of your research? I'll blindly say aerospace. But how effective is that? Because for parts that must um, that go into rockets or that go into jet engines, there is a rigorous qualification cycle. And as we might already be aware, or for some others, as we'll come to know gradually, the parts that come out as built from the additive manufacturing process often do not have um, the most desirable properties. They might even have defects. They might not be as dense as, say, they were designed to be. And thus, say, large-scale application of additively manufactured parts in the aerospace industry, it's a process in the making, but we are not fully there yet. Similarly, for automotive parts, healthcare, of course, because of the vast potential for customization, patient-specific customization, healthcare is one of the areas where additive manufacturing is bringing in big and significant change and saving lives, I must say. And in the next, say, 6 to 7 years, by 2031, we see that all of these industries will be rebalanced, and the impetus of AM will specifically be towards aerospace, as it already is, and also healthcare. There are no numbers in the y-axis for this plot for some reason. Okay, so let us recap the course contents for this week. First, we went over the various um, terminologies and terms that are used to define the additive manufacturing process. I mean, for some of us who are in academia, either as students or as teachers or as researchers, you might have come across terms such as, say, DED, SLS, SLM, DMLS, even lens, and so on. Now, each of these terms actually define a type of additive manufacturing, but the terms which are used to refer to the very process itself are listed here. So, 3D printing is one such term, which is perhaps the most popular and the most commonly used. Academicians like to use the term additive manufacturing. However, let us keep in mind that all of these terms are referring to the same thing. And similar to additive manufacturing, sometimes the terms additive layer manufacturing is used or additive digital manufacturing is used. And similar to 3D printing, sometimes the term stereolithography is used. Lithography, as we know, is something similar to writing. And when we add the term stereo to it, just like how a stereo microscope allows you to envision an object or a specimen in three-dimensional space, stereolithography perhaps refers to writing in three-dimensional space or printing in three-dimensional space. Layer manufacturing is another system, or layer-based manufacturing or layer-oriented manufacturing, primarily because by definition, all additive processes should proceed in a layer-by-layer fashion. Then there is solid free-form fabrication. Free-form referring to the complexity of geometry and the various degrees of freedom that the process offers us, so that we are able to manufacture objects which can be freely of any shape without much geometrical constraint. Digital manufacturing, because again, by definition of the process, it must say start from a digital source. It must start from a computer-based model, as we'll see. And similarly, the term digital mockup, and a term which was really the rage in the late 90s and early 2000s, which is rapid prototyping or rapid manufacturing. Rapid prototyping because one of the early applications of this technology was to make prototypes of a product because before it went into a full production cycle. And similarly, other terms which are used are direct manufacturing and direct tooling. And as Professor Kapil had given a very nice example, the term 3D printing is simply an extrapolation of 2D printing. In 2D printing, you are printing along, say, the X and Y axis of the sheet of paper. The paper is a plane. So you're just moving and printing along the X and Y axis. Whereas here we are printing in space. So say if I affix an origin to this stage, I have an X and a Y axis, but again, I also have a Z axis. Now this Z axis may be attached either to the build plate, in which case the build plate, the deposition head moves in the X and Y directions, and the build plate changes its height with every layer, or the Z-axis may again be given to the deposition head itself, whereas the XY axis lies with the stage. So in each plane, the XY axis will move, whereas for each deposition, the head will keep rising by a fixed distance. Now here is the formal definition of the additive manufacturing process. So AM refers to the layer by layer fabrication of three-dimensional physical models directly from a computer-aided design. It is an automatic process of manufacturing objects such as parts, prototypes, tools, even whole assemblies directly from their CAD models without the use of any cutters, tools, or fixtures which might be specific to the object geometry. Now, the definition is important because it helps us it helps us distinguish between processes and characterize whether they fall into the additive fold or not. So typically in a conventional manufacturing paradigm, you would need fixtures and tools that are specific to the type of job that you're trying to manufacture. Say if you are working with a cylindrical job on a lathe, a three-jaw chuck is suitable. Whereas if your job suddenly becomes cubical or cuboidal, you cannot use a three-jaw chuck anymore. It must be a four-jaw chuck. Similarly, depending on the type of operation that you're performing, whether it is milling or cutting or drilling, the type of tool that you're using will change. However, additive manufacturing is free from such restrictions, and it is truly a free form fabrication because the same setup, the same machine, the same deposition head will work um, irrespective of the geometry of the object, however complex it might be, and irrespective of the final um, part that you envision in your mind. And on the right here are some of the primary processes that are involved in the additive manufacturing paradigm. First, given it is a digital process, we do the pre-processing where we sit at a computer, we design our CAD file or CAD model, or in case that you are just running a manufacturing unit and the client gives you the CAD file, you tessellate it. Tessellation is a process of basically covering the surface of the object by a series of triangles. The triangles are well connected to each other and they approximate the surface of the given solid to the extent that you define. So you have control over the tolerances in this case. The finer triangles you use to tessellate the surface, the more accurate the representation of the initial solid. However, it will always be an approximation in case of complex geometries, whereas for simple geometries, the representation may still be exact. Then we slice the tessellated STL file. Slicing because, as we read in the definition and as we have been discussing, the additive process is a layer by layer fashion, layer by layer process and proceeds in a layer by layer fashion. So as you see in the example here, the entire sphere was first tessellated or covered in these triangles, and then this tessellated file is sliced by all of these planes, as you can see. And what will happen is, in each printing pass, the intersection of this tessellated file with the plane will be printed or deposited or sintered, depending on the process that we are undertaking. Then the deposition head will move up or the stage will move down by this fixed uh, height of each layer, and then the next intersection of the slicing plane with the tessellated file will be deposited. But of course, first, this slicing tessellation and the generation of supports is being simulated in a computer. You're visualizing if there are any changes to be made, how the tolerances should be tuned to best achieve your end goal. And once we are satisfied with this pre-processing, once our work on the computer is done, we move on to the actual building of the part in our machine, which is in an additive fashion or a layer by layer fashion, which is accomplished through the stacking of successive layers. And then in most cases, you would require a post-process or a post-processing step where if you have generated supports, you might need to break them away or in certain cases dissolve them in certain chemicals. You might need to finish the surface of your finished part because the surface tolerance and the surface finish might not be to your desired level. Or in certain cases, if the density that your as printed part has does not qualify for the client's requirements, you might even have to say undergo a step such as hot isostatic pressing to improve the density. We see the term support here, and let us try to understand when supports come into the picture and what is their role. Here is an example of a water tank, which is typically made out of concrete. And this water tank has two sections. One is this supporting column, and the other is the part of the tank itself, which is like an overhang. Overhanging because it does not have any support structure directly supporting below it. So it's as if the structure has been built in free space without any support, out of thin air. Now, we see these structures all around us all the time. But at the time of their construction, they must be supported by, for example, the bamboo scaffolding that we see here. Once the concrete has solidified and hardened sufficiently, the support structures may be removed. And similar is the case for additive manufacturing. That is, for geometries which might have significant overhangs, we might need to support them with additional support structures which are not really part of the original intended design, and thus they will have to be removed. And since we have to remove them later, of course, an intelligent guess would be to make them, say, maybe not as strong as the core part, or to make them thinner, or say less dense, or even hollow, so that the removal is easier. However, they must still be strong enough to support the product. Here again, the instances of deposition of material on a flat substrate are illustrated. So when the deposit is being, a material is being deposited, say in the bulk or in the middle of the substrate, there are no problems because it is supported on all sides. However, when we are depositing near a corner, the dynamics will be such that there is the weight of the droplet or the material acting, then there is the surface tension acting on the surface of the molten material. Also, there is a normal reaction. There will be frictional forces and so on. And the interplay of all of these forces or their balance will decide whether this material is able to rest on the substrate or it falls off. In the example here, we see that if the overhang is large, or in simple terms, if a larger portion of the droplet is without a support, there's a very good chance that it might simply fall off. And one can also imagine that even if, say, for the first layer, the material was able to be sustainably put on the substrate, with consecutive layers of build-up over this overhanging part, there might come a critical point where the pre-deposited layer is unable to support the load anymore and the structure collapses. We'll be touching all of these aspects in great detail as we move through this course. Uh, some greater insight into the term digital manufacturing. Now, digital manufacturing is actually used to refer to the set of technologies which can reduce the product development time and cost, as well as are capable of addressing the need for customization, increased product quality, and faster response to the market. Let us discuss each of these terms one by one. So, how does additive manufacturing help to reduce the product development time? We will come across a flowchart of product development where we will see that the typical or conventional cycle actually involves multiple iterations of designing, refining the design, uh, making a prototype. There are lead times involved everywhere. Then corrections are to be made, toolings are to be designed, the assembly line, the production line has to be customized to each product. And after a few iterations, we end up with a final version of the product, which can then go into mass production. However, with AM, most of these complexities are alleviated. How can additive manufacturing reduce the cost? Now, when you are trying to manufacture simple parts, conventional manufacturing is the way to go, plain and simple. There is no replacing conventional processes. And it is very important for us to understand that additive manufacturing is not a substitute to conventional manufacturing. I mean, if you just want to print a simple, say, a cuboidal plate, if you just want a simple cuboidal plate, you will cut it out of an existing plate, or you will form it, or you will maybe machine it using water jet, or from a bigger block, you will maybe face mill out and then end up with this plate. You will not go and manufacture it in a powder bed facility because the costs are simply not justified enough. However, if you want a lattice structure, even say the simplest hollow lattice, now this is very difficult to produce by conventional manufacturing method, and you better resort to an additive process. So for parts which are more complex and which are highly specific to its user base, the costs can indeed come down with an additive process. Customization, as we discussed, we can make the design to suit a specific patient in the case of implants. You don't need to adapt your production line as per the needs of each patient. Increased product quality, well, debatable, given that most times the product coming out of an AM cycle still need further post-processing and need to be qualified rigorously. Faster response to the market because of the immense flexibility and adaptability, as we'll see. And a manufacturing technology can be called digital if it is centered around a computer system. And as we saw, our very production starts in front of a computer, and we'll spend a good amount of time optimizing the production in the computer. Thus, AM technology fulfills this criterion. And just like a digital image is made out of two-dimensional elements called pixels, the same analogy somewhat is extended to the case of STLs or standard tessellation language files or stereolithography files, as we'll see. So here we see the bust of a human head, and it is being approximated by a series of triangles. So here the triangles are rather coarse. Here they are medium, and here the triangles are fine. As we decrease the size of the triangles, their number increases to cover the same surface area, and the accuracy of the representation is increasing. While it is still an approximate representation, we see that the final outcome, in this case using very fine triangles, is much closer to the actual three-dimensional geometry. The STL file format uses a series of linked triangles to recreate or reproduce surface geometry of the 3D model. The more triangles used, the higher resolution of the 3D model, and The STL file is perhaps the most commonly used and the most widely accepted file format in additive manufacturing industry because it is quite simple, it is light, and it is very easy to be handled and universally accepted by 3D machines and 3D printing software. As we discussed, an important step of the additive manufacturing process is the slicing of an object using parallel planes. But as one may imagine, if we are only printing in a plane at a time, and say we slice this object to the left here using such planes, so say I used a series of planes to slice this object, and we deposit material in each plane, what we'll end up with is akin to the right. So say here is layer 1, layer 2, then layer 3, layer 4, layer 5, and so on. And thus, you will see that compared to the original geometry where you had curvature over this face, now you end up with something that resembles a staircase. And staircasing is one of the well-studied and well-known problems of an additive manufacturing process. And we'll look at some of the few strategies to calculate this staircasing, minimize it, and maybe even overcome it in certain cases. Now, the distance that we use for slicing, or the interplanar distance, or the layer height, whichever way you want to visualize it, has an effect on the printing time as well as the print quality. So, if we are using uh, more spaced or uh, planes which are spaced apart more, the layers we'll end up with will be thicker. And so in each printing pass, we can deposit more material, have fewer passes, and print our material in less time. So thick layers print fast. But look at the resolution that we are getting. In regions where the geometry is simple, such as say around these legs, it's okay. But in regions of high curvature, such as the back of this rabbit, the approximation is very erroneous. Now we can have thin layers for a higher resolution, and we see that here the curved parts, such as the back, the ears, and the face and mouth of this rabbit, are well represented. The time that it'll take us to print this will be far, far longer. And in a commercial process, in a commercial setting, in an industrial setting, time is money. So perhaps the solution is to be flexible, just like the additive process, and to use something called adaptive slicing, where we intelligently identify the regions which can do with, say, a coarse slicing, such as these layers at the bottom, and then regions of high curvature which need fine slicing, such as all of these other regions that we highlighted before. And use a combination of the two for optimum time as well as optimum resolution. The objects that are fabricated by joining these thin layers by a suitable method of our choice is a generic process, and it is completely automatic. It is not dependent on the geometric complexity of the material, the difficulty in machining the material, or for the need to design special fixtures and special tools. Now here we have an example that illustrates rapid prototyping versus virtual prototyping. And based on this, I would say excellent classification on whether a prototype is physical or virtual, or whether it is a component level part, or it is a complete assembly, and how accurate or rough the representation is, we can end up with uh, different stages of development. So if it is a physical part, but only of a component level, and it is complete, we can end up with a foam model of a car. If it is physical, it is very accurate and complete. It is the final product itself, as one would say. If it is just a virtual representation and a rough representation, that too, a sketch suffices. And if it is complete but virtual, it's the CAD model of a car. Here we have a flow diagram illustrating the relationship between virtual prototyping and rapid prototyping, and Professor Kapil explained it pretty well. Let us also familiarize ourselves with the capabilities of the AM process, and in the duration of this course, also the limitations of the process. So AM refers to layer by layer fabrication of three-dimensional physical models as we study, and the primary capabilities that we'll be looking into are the geometric capabilities and the material capabilities. Now, let us consider this hinge assembly that is given here. If we were to proceed via a conventional route and manufacture this assembly, we'll first maybe have to manufacture each of these individual parts. Five are listed in this case: one, two, three, four, and five. So four and five are of the same type, so maybe they'll have a similar production setup. But for the others, you will have dedicated production lines, dedicated designs, machining processes, tools, fixtures, and so on. And tomorrow, if a new standard comes up, or if a new design of, say, a door hinge comes up, which is better or more popular, you will have to adapt your production line in order to be able to manufacture the new product. On the other hand, on the right side here, we have manufactured a similar assembly using an additive process, and it's a one step. And from the look of it, this looks like a fused deposition modeling or a polymer 3D printing process, where you can manufacture this entire assembly in one go, in one cycle, without the need for any post processing or minimal post processing at most. Why is this similar to the conventional design and not exactly the same? It is because of something called design for additive manufacturing, whereby we adapt our design to have the same functionality, because that is paramount. We can't really change the functionality. So say it should have the same strength, it should have the same number of degrees of freedom, and so on. But we slightly tweak the design to exploit the benefits of additive manufacturing and to overcome any limitations. Say if you have large overhangs, you would like to minimize them. Thus, the same part can be produced additively and via conventional routes, and each will have its own features. In the duration of this course, as we cover each process step by step, we'll find out what the specific limitations are in each case. Again, in terms of geometric capabilities, another example which illustrates the high value of the additive process is the manufacturing of these conformal cooling channels when you are, say, casting a part. So typically, you will have these parallel cooling channels along the ends of the mold, and you will have water or any other coolant of choice circulating. Say it goes in one way, comes out the other, but it's not really suited to the type of part that you're trying to manufacture. Whereas in an AM process, you can actually have these conformal cooling channels printed around your part itself, and to suit the specific geometry or the customization that you're looking to manufacture. For example, in this case here, we are trying to print this mold, and what we can do is we slice this geometry. So if I slice something like this along this plane, maybe I'll not deposit material in the center. Wherever my cooling channel is supposed to be. And for the rest of the part, I will have material deposited. And the dimensions of this, say, region with no deposition will vary with the change in cross-section of the part. Another geometric capability is the flexibility for mask customization. So the image that we see here are a number of keys, each unique or at least in sets of three, which as we see can be largely simple, such as the key here, or more complicated, such as the keys here. But all of them can be printed in the same bed, in the same cycle. And depending on which parts are getting completed layer by layer, say in this nth layer, all of the parts have to be printed and they are illustrated in purple. In the n plus 1th layer, some of the parts, such as ones that are highlighted in black, are completed, but the others that are hatched in purple continue to be built. So what we'll have is maybe if we are going through a powder bed process, we'll just have powder over these finished parts, but not run our laser in those regions. Simply sinter or melt the powder in regions which are still left to be manufactured. In the N plus 2th layer, we see that most of the parts are already done and they are highlighted or color coded in black, whereas some other parts which might be thicker and are hatched in blue and purple continue to be printed, and so on. We can continue and build a large number of highly customizable parts in the same cycle. Whereas if you are going through a conventional manufacturing process, you would be able to say even just produce only one type of keys in each cycle. Now, other geometric capabilities may be such as the lattice structures, which are one of the most, say, well-cited and illustrated examples of AM capabilities, where you want to have these hollow structures which are super strong and have a very good strength to weight ratio, and are widely used in lightweighting applications. But imagine trying to make these via a conventional manufacturing route, and you will really suffer because often it's not possible. And in cases when it might be possible, it is still very tricky, very time consuming, and a high cost process. Whereas additive processes simply excel at such application of low volume and high customization. Then additive manufacturing can be used to make functionally graded materials. So FGM stands for functionally graded. And this is a concept borrowed from nature. So here we see the example of a human bone, where you see that the bone, as we know, is not really a solid structure through and through. The outer layer of the bone is very dense and very hard. In the middle, it is somewhat hollow and spongy. And in the center of the bone, it is totally hollow and instead filled with bone marrow. Now, just then, like this is a part which say varies radially in its density and strength. Using additive manufacturing, we can also build parts which may vary along any chosen direction of ours, such as radially or along any of the Cartesian axis, in density, in hardness, in the very material itself that we're using to build it. And we'll see some examples as we go along. Some of the materials that can be processed by additive manufacturing are listed here. I'll not go through the entire list, but as you can see, a wide gamut of materials is covered: polymers, ceramics, food materials, pure metals, alloys, high entropy alloys, and so on. Functionally graded materials, as we discussed. Here is the application of, say, the nose section of what appears to be a space rocket. Now, these rockets are subjected to very extreme service conditions. The nose itself may be subjected to very high temperatures, drag forces, large friction forces, and even its service conditions may range from below freezing temperature to vacuum, to very high temperatures generated as a result of those dissipative forces that we discussed. And thus, you'll rarely find one single material which performs well under all of these conditions. Now, coatings have been previously used to suit such an application, but say you have this metal part and you coat it with a ceramic layer, but then this coating is a tricky process. It is costly. Um, Not all coatings are compatible with all surfaces. Your surface might even require some, say, pre-processing. The coating being very thin is vulnerable to damage. It can be scratched off, and then it can come off as well. Then again, because of the vast difference in the thermomechanical properties, such as coefficient of thermal expansion, the specific heat capacity, the thermal diffusivity between the coating material and your base metal, the interface between the two will be highly prone to cracking, to corrosion, and in general will be the weakest part of the whole structure. The strategy which can be implemented using an additive process is something akin to an FGM, where we have a gradient in material along the radially outwards direction. Thus, the core is made out of metal, whereas the outer layers are made out of ceramic, and there is this transition zone in between. Another example of changing material being this colorful object, where depending on the location, we have used or the authors have used different colors to build a part. These colors are not just on the surface but through and through because the material or the filament used to build them were different. Some other examples, a transparent object and another colorful object. And finally, the classification of the additive processes into various categories. So as per ASTM, there are 7 major types of additive manufacturing processes, and all additive processes may be classified into any of these 7 types. The first is vat photopolymerization, where you have this vat of a resin or similar material full of it, and your stage moves down in each step. We use a UV laser, say typically of some 40 to 50 milliwatts. The laser scans on the surface of the resin and cures the area of interest. Then the stage moves down by a pre-decided layer height, and the process is repeated unless we end up with the fully built part. Now notice here that the laser assembly is on top, and so the stage is moving down, but it might also be the case that in some cases the laser is coming from the bottom and the stage is moving up. We'll examine what the advantages and disadvantages of either configuration is later in the course. The second ASTM classification is material jetting, where you have these material droplets in green. I'm going to write material droplets in green being dispensed by this printing head, and in blue here what you see are the curing rays, which may be UV. And in each case what is happening is the deposition head is, say, scanning from left to right. It is dispensing the material that is to be printed, and it is followed by this scanning by the UV rays, which cures the material in place and builds a product layer by layer. The next case is binder jetting. So previously we were dispensing the building material itself. Now we are just dispensing the binder material. Binder is something which holds your building material together. So in this case, say the vat or the tub is already full of the building material, and you are just selectively dispensing the binder layer by layer as the stage moves down, and only those regions are hardening up to form the part. Professor Kapil cited the example of cement and water, how cement is the construction material and water can act as the binder. So if in a layer of cement, you selectively dispense water in selected regions, only those regions will harden up. And if you perform this accurately, layer by layer over many layers, you can end up printing a three-dimensional part. The next class of processes are the material extrusion type processes, such as your fused deposition modeling, FDM. And in this case, you extrude these wires using at least a pair of rollers, sometimes even more. Then these set of rollers help you in controlling the extrusion rate or the rate at which you want to supply the material. You have a resistance heating zone where you utilize resistance heating or joule heating to say reach temperatures of the order of 200 to 300 degrees Celsius, which are sufficient to melt or at least bring into a semi-molten state the mostly polymeric materials which are used in this case. And another advantage, as you can clearly see, is you can even end up using two or more materials. Manish, could you please mute yourself? Thank you very much. So you can end up using two or more materials to build products of multicolors, or in certain cases for complex geometries with overhangs. One material can be used as the build material, say the red one. The other one, that is black, can be used as a support material. The next class of processes are referred to as sheet lamination and also laminated object manufacturing. And this is an interesting one, but alas, is less explored compared to the other processes. In this case, your feedstock is a sheet, and you have this roll of sheet that you're unwinding slowly and winding it on the other side. You spread it over your region of interest, and a laser or say any other energy source of suitable power scans this area to mark out the region of interest. Say you're trying to print some simple geometry like a star. Your laser will scan over this region and cut out this star from the sheet. And then using some mechanism such as a thermally activated glue or ultrasonic means, as we will see, this sheet of or this layer of the part will be fused to the previously built layers, and then the remaining sheet will be rolled out. As you can clearly see, it is not a purely additive process because there is this subtractive step or the machining step involved. Thus, all laminated object manufacturing or sheet lamination processes are by default hybrid type of processes. And there are two paradigms in this case, form then bond, bond then form. We'll talk about it when we come to it. The sixth class of processes is the powder bed fusion type processes, which are very well studied and also known by names such as SLS, SLM, DMLS, and so on. In which case, you have these reservoirs of powder on either side. So maybe these can be reservoirs, or one of them can be a reservoir, the other can be the sink. You have something akin to a doctor's blade or a roller, as per the geometry, that dispenses the material out of the reservoir onto the area of interest, spreads a uniform layer of it, and then you use a laser or say in some cases an electron beam or any other source to selectively scan the region and build your material layer by layer. And here you also see that in regions which had overhangs, such as this, you have these support structures that are also built in order to support the part that you're building. Powder bed type processes generally have very good dimensional accuracy. The parts also have good density. However, the build times can be larger depending on the size, and the build volumes are restricted, so you cannot really build very big parts. And the seventh and final class of processes is the directed energy deposition type or the DED type processes, where you have the material being fed, in this example, in the form of a wire, and you are using certain energy, say a laser source or an arc, to melt this material and to also melt the pre-deposited layer or the substrate and to fuse these two molten materials strategically to build a part of your interest. Now, DAD processes might not have the geometrical accuracy of, say, a VAT photopolymerization or the PBF-like processes, but they do have higher build rates. And in most cases, I mean, depending on the machine that you have, the volume of the geometry that can be deposited or built can be quite large. There exist even machines that can build scaled rocket parts. So we are talking parts that are 2.5 meters long or high in one go. However, as we discussed, the dimensional accuracy or the surface finish might not be as good. And so depending on your budget, depending on your application, depending on the desired quality of the product, you will have to choose whether you want to opt for a conventional or an additive process, and if an additive process, which one of those. And the processes are classified by ASTM based on the increasing energy consumption. So on the left hand of this spectrum is VAT photopolymerization, as we discussed, which uses UV lasers of the power of, say, few milliwatts, few tens of milliwatts, like 40 to 50 milliwatts. In powder bed fusion systems, typically you'll have lasers that are, say, close to 500 watts. In DED processes, your power ratings can be anywhere of the order of, say, 4 to 8 kilowatts, perhaps even more. However, for this course, as Professor Kapil pointed out, we'll be following a classification that is based on raw materials. So based on the type of raw stock, whether it is liquid, solid, or gas, we classify the processes and study them. And for gases, there is no, say, explicitly designed or explicitly explored additive process as of yet. There are some that come close. So I have read a few papers where they use or they propose to perform nano additive manufacturing using aerosols. So aerosols are not technically gases. It consists of uh, particles that are dispersed in a gaseous medium, but it is getting there. And you use these aerosols to form highly controlled nanostructures with myriad applications. So let us quickly move on to the second one, and then we can get to solving questions. In the second lecture of this week, we were introduced to the concept of solid modeling. Of course, most of us would have done a few courses on solid modeling, even be familiar with a few CAD softwares such as AutoCAD, SolidWorks, or CATIA, or so. Still, for the sake of completion, solid models are known to be complete, valid, and unambiguous representations. And a complete solid is one which enables a point in space to be classified relative to the object, whether it is inside, outside, or on the object. A valid solid should not have any dangling edges or faces, and an ambiguous solid has one and only one interpretation. It is not subjective. The two important aspects of any solid model are its geometry and its topology. Geometry refers to, say, the dimensions of the lines and the arcs. Um, and here we have cases. Topology, of course, refers to the way these lines, these vertices, edges, arcs, they're connected to each other. And here we have a very good illustrative example where we have two figures. On the left, they have the same geometry in case that L1 is equal to L1 here, L2 and L2 are same for L3 and L3. The length of the arc C1 is same in either case. The radius of curvature R is also the same. But in one case, the point P1 lies on the outside of this object, whereas in the other case, P1 lies inside. So while they have the same geometrical lengths or measurements, they are connected differently, thus leading to a different topology. Whereas in the case to the right, they look kind of similar, but geometrically they are different because, say, as an example, the angle between L1 and L2 here is not right, whereas here it is equal to a right angle. Also, L1 or L3 might not be the same as L1 and L3 of the top figure. Thus, they have similar topology or the same topology based on the interconnectedness, but different geometries. And some of the popular methods of representing solids are constructive solid geometry or CSG, where you have these basic solid objects called primitives, such as cubes, cuboids by extension, cylinders, cones, and you perform Boolean operations using a combination of these primitives to come up with the final part of choice. Second is boundary representation or BREP, where you represent any solid in terms of the surfaces. Third is the feature-based modeling, where you use features such as sweep or extrude and other similar operations to come up with the solid geometry of your choice. A software which is very popularly used called SolidWorks uses feature-based modeling. Then there is something called space decomposition. And of course, if you're using a combination of any two or more, what you're performing is actually hybrid modeling. Now, Professor Kapil has already talked about all of these, so I'll be skipping over these for now. And as we discussed in the from the previous lecture, for most of our additive softwares and additive applications, we'll be requiring the CAD file to be in something called an STL format. The STL format, in fact, derives its name from the term stereolithography, which was the very first additive manufacturing process which was commercialized. And over a period of time, it has been expanded to be more general to the additive process and has been expanded as standard triangle language because we use triangles for tessellating our surfaces and also as standard tessellation language because of the tessellation process. The STL file format encodes a surface geometry of a 3D object using the concept of tessellation. And here we see examples of tessellation where we have covered surfaces such as the walls of our house using these triangles. In some of our houses, the floors may be covered by such square tiles. This is also an example of tessellation. This curved wall is again covered by these rectangular slices or rectangles, which is again an example of tessellation. Tessellation simply refers to covering a surface such that there are no overlaps and no gaps. STL is a faceted boundary representation model which approximates the model surface by a series of connected triangles. It does not contain any information related to the color, the texture, density, or say even the material. It only has the surface information. The STL file describes the raw unstructured triangulated surface by representing each triangle in terms of its unit normal and by defining its 3 points. And of course, we can for any surface we can have two normals. One is the outward normal, one is the inward normal. In the case of STL file format, we define the outward normal, and its definition is that along the direction of the normal, there is no material present. So, say behind this normal, there is matter. The question, of course, then arises, why triangles? What makes them so special? So, any three non-collinear points form a triangle, and to define a plane, you need only 3 points. We are well aware of that. Every triangle forms a unique plane, and triangle points cannot be part of two planes. Thus, there is no ambiguity and there is no problem of dealing with multiple solutions or other computational errors. Any surface or any geometry can be broken down into triangles, and if you end up with triangles, triangles can only be further broken down into other triangles. This triangle is the most versatile and the most universally flexible shape. The occasion might arise where we have to compute the mathematical equation of the triangular surface, or in simple terms, the plane that a tessellated triangle is approximating. And here is the equation for that. We'll also be touching on an example during our problem solving time. The STL file basically contains a set of oriented triangles. And as we discussed, it has information about the unit normal. So in terms of its components, nx, ny, and nz for the right triangle, and the points. So for each point, you have the x, y, and z coordinates. The file lacks any topological information like links, pointers, or other. It only contains the geometrical information. And each vertex is written by its coordinate as many times as it occurs in the mesh. This may lead to problems as mentioned here, because in computations there are a round of errors, and these errors may compound over time based on repeated or iterative recalling of these points. And often there might also be truncation errors where we are not using the same levels of precision in calling these vertices every time. And over time, what may happen is these errors add up and they cascade quickly to computational errors. Also, STL does not contain the dimension units. What you have is a parametric representation and it is easily scalable. On the downside, you don't really know what dimensions you're working with. And typically, STL files can either be in the binary or the ASCII format. The ASCII format being more user-friendly, the binary format being more machine-friendly. Here is a quick example for partial representation of a sphere by in an STL format. So you start with the term solid and the name of the file, in this case sphere. Then for the first facet, so say this is facet 1, you have first information about the facet normal in terms of its unit coordinates or unit components. And then within a loop, you have information about the vertices in terms of their XYZ coordinates. Similarly, for the other facet, say facet 2, and so on. And when ending the file, we use the keyword end solid. The group of the three vertices defining a triangle are delimited using the terms outer loop and end loop. And we will systematically list these triangles in the counterclockwise fashion, so that by using the right hand rule, one can find the direction of the facet normal. Remember, the right hand rule is what we utilized to find the direction of the vector cross product in case of vector multiplication. And if you're already listing the vertices in a counterclockwise fashion, as you can pretty much figure out, even the information regarding the facet normal is somewhat redundant. We will look at an example where we must calculate the unit normal of a triangular facet later. And it has also been shown via some simple calculations that the information about the facet normal is indeed redundant and it can be calculated from the information about the vertices. Professor Kapil also illustrated how to write an STL file for this unit cube that we have here. I'll not be covering it again. And he shows how, since you have six square faces, you divide them into 12 triangles, and how you write a facet loop for each of these 12 facet triangles, and how you end up with a final STL file. In each case, we should be careful to list the vertices in a counterclockwise fashion. The exact sequence does not matter. Say, if I name these points A, B, and C, it is not always the case that I must list them only as ABC. BCA or CAB are equally correct because they all have the same sense, same counterclockwise sense. The other format for storing STL files is the binary format, which is more machine friendly and it has the following characteristics. So an 80 byte ASCII header file, which is used to describe or name the part, the 4 byte long integer for indicating the total number of triangles, and each facet will have 50 bytes allocated to it, 3 floating or 4 bytes each for the normal vector components. Now 3 floating values of 4 bytes each for the first, second, and third vertex, and one unsigned integer of 2 bytes, which should be 0, which is used as a check to see whether the file is proper or whether it needs repairs. And here is an example of such a binary STL file. Professor Kapil also walked us through this and showed how and what each line of the code means. I'll not be doing that again. And as we previously discussed, depending on the size and number of triangles that we are using to approximate a surface, the mesh we end up is either a coarse mesh or a fine mesh. There is always a trade-off between the accurate representation and the number of triangles used. The larger the number of triangles, the larger the file size. Some of the parameters which are used to quantify this accuracy are deviation tolerance and angular tolerance. So deviation tolerance is measured in terms of the chord height. It is the maximum deviation between the designed part and its STL representation. And the chord height is basically the perpendicular distance or the maximum perpendicular distance between the actual curve, which is given in green in this case, and its STL representation. Of course, as we see, this error varies along the curve, but we are looking at the maximum perpendicular distance. And if we choose the right or the optimum tolerance, the printed part will look very smooth. It will have a good finish. The smaller the chord height, the more accurate the representation. And as a rule of thumb, it is recommended to set the chord height or the deviation tolerance between 0.01 to 0.001 mm. This results in good quality prints. If we were to think that we can keep on decreasing the deviation tolerance monotonously and end up with better and better parts, there is no point in reducing this further because in most cases our 3D printers will not have the resolution to print at finer details. We'll be looking at examples on deviation tolerance during our exercise. Again, the angle tolerance controls the maximum angle between the normal vectors of each triangle. And in this case, we can have a monotonously low value. So the smaller this value, the better. We'll also be looking at an example on angle tolerance. And here are some of the topology rules which Professor Kapil went over. Let us not repeat those in the interest of time, and let us focus on the mathematical errors which can arise in such a tesseract representation of any surface. Now, the computation of the line of intersection of two intersecting surfaces can lead to errors in knot-to-knot connection vertex shared by the triangles lying on certain surfaces. And as we discussed, given that we are representing each of these triangle vertices by float values, depending on each iteration, the truncation errors and round-off errors may lead to cases where there are gaps between these triangles. They do not really, the same vertex is called differently for each triangle, and they do not really meet at a point. Often due to a higher tessellating resolution, smaller triangles are generated and the triangles may collapse into a line. So if we are trying to break down a surface, say we have a triangle, we are trying to break it down to obtain a finer and finer mesh. This is a case where we break it down into two. But if we start to have our tessellating triangles finer and finer, you can well visualize that there will come a time when the aspect ratios become very large and the two vertices of our triangle coincide and the edge simply disintegrates or degenerates. Thus, we can't have an arbitrarily fine mesh. Also, high degree edges can be generated and shared by multiple triangles and at tangential points. So some of the errors to look out for. We are done recapitulating. So why don't we take a short break of say 5 minutes and then we'll start with our problem solving session. So I'll see you all in five. Hi and welcome back. So let us continue with our discussions. And now we'll look at a few questions. The first question related to fundamental understanding of the additive process. And it asks us that in the case of functionally graded materials, variation in which of the following properties may be observed. So feel free to unmute and answer if you feel any of the options are correct. The first option is density. As we saw in the case of human bone, the density does vary as we move radially inward or outward. So the outer casing is really hard and dense. Whereas in the intermediate region, it has a spongy structure, so a lower density, whereas in the very middle it is hollow. So density is indeed true. What about material composition? So we looked at the case of uh, the nose part of aerospace rocket, which was made out of metal towards its core, but towards the outer edge, it had some ceramic infused into it. So even the material composition or the material chemistry may change. Porosity, as we noticed in the case of that lattice structure, which, if I may go back to that slide, which had larger cells here in the central region, whereas in the intermediate region the cells were smaller, and on the very edges we see these closed cells. So once again, even the porosity might change, and as a result of the material composition or the density or the porosity, even the mechanical properties may change. And what additive manufacturing allows us is to actually tailor each of these properties, be it the density, be it the porosity, be it the mechanical properties, or even allows us to utilize the very material itself as a spatial parameter to form these functionally graded materials. Thus, in this case, all of the options are valid, and this is how it will be in general. So more than one options may be correct. The second question is related to one of the AM processes that fall into the broad classification that ASTM has laid out, specifically the directed energy deposition or the DED process. And the question being asked is, what is the feedstock material for a directed energy deposition process? Is it powder? So typically, if we look at uh, additive deposition head, we see that in certain cases, in certain arrangements, we have the laser coming out of the center, and from the sides, we have these streams of powder. Of course, in this view, we can see two, but they may be four to six or even more, depending on the configuration that you have, and it will get deposited on a substrate. So powder is definitely true. I mean, powder DD is pretty commonplace. Filament, not quite, because filaments are used more in the extrusion type processes, so more like FDM. Liquid, it will be difficult to transport liquid in a direct energy deposition process because typically we use a carrier gas for carrying powders. With liquid, it gets more complicated, so liquids are typically used in processes such as, say, VAT photopolymerization. What about wire? Is wire a feasible feedstock material for a direct energy deposition process? And if you go back to the slides, sorry, I'm going the other way. We see that in the very example that we see here, wire is the feedstock material that is being used in a DET process. And in this case, it might very well be that this is just the retrofitment of a welding gun on a CNC machine that is giving us this setup. So wire is an equally valid choice of a feedstock material for the directed energy deposition process. Thus, in this case, both powder and wire are suitable. An objective type question: what is the wavelength of the laser used in wet photopolymerization? And here we don't really have the exact values, but more like the range of wavelength. So whether it falls in the infrared range, whether it is in the visible range or the ultraviolet range. We know that for wet photopolymerization, our feedstock material or the raw material is in the form of resins or polymers. And the energy source which cures these resins is in the ultraviolet range. Thus, the correct option here is ultraviolet. The next question is comparing additive and conventional manufacturing processes, and we are asked to reason which of these options may be true. So, the first option says that additive manufacturing can fully replace conventional manufacturing. Let us examine how valid this statement is. If I want a cranial implant for a patient who was in an accident, and I have a reconstruction of the patient's original skull, and I want to place an implant which is close in shape, size, and geometry to his original skull, will I opt for a conventional manufacturing process? Probably not. I'll go for an AM process because I already have the CAD reconstruction of the patient's skull, and with AM, I also have the capabilities to manufacture a part which will be very close in terms of geometrical approximation to the patient's skull. But if I want a block of material, say a cuboid, will I get it machined out of a larger block or will I 3D print it? What makes more sense economically and from the perspective of common sense? Of course, I'll opt for a conventional process. Thus, AM can never truly or fully replace conventional manufacturing. Conventional manufacturing processes are superior to AM, says option C. Clearly not, because for the past hour or so we have been expounding the superiority of AM process or the specific use cases where AM processes are the only choice and where conventional processes fail. So both options A and C are wrong. Option B suggests that additive manufacturing might just be complementary to conventional manufacturing, and you can choose between both depending on your requirements in terms of the material that you're using. Is it difficult to machine? In terms of the tolerances that you want, in terms of the geometry that you're looking to recreate, in terms of the customization that you expect to encounter in the future with the similar production line, among others, and the budget that you have. And this budget may be drawn out by the capital investment on technology, the skill that you need, the power consumption, the cost of the raw feedstock. You take both of these factors into account, if not more, and then you make a choice whether you opt for a conventional process, whether you opt for an additive process, or whether you combine both of them. Thus, option B in this case is the correct option. The next question is asking us which of the following processes may be classified as an AM process? And the processes laid out are DED, optical lithography, and investment casting. Now, DED, of course, I mean, we have just been talking about it. Clearly, it is an additive process. Yet, let us go by the definition and check. So, it is the process of joining materials to make parts from a 3D model data, usually layer upon layer, as opposed to subtractive and formative manufacturing methodologies. In DED, we do join materials. We do start with a 3D CAD model. We perform this operation layer by layer, as you can see for this apparently a cube which is being printed here. So you see these multiple layers in each case, the boundaries of the layers. I'm just highlighting for your easy reference. So it is indeed an additive process. What about optical lithography? So we have something akin to a substrate. We have a layer of photoresist. So the layer by layer thing is also coming into the picture. Then we expose it to some energy, in this case in the ultraviolet range, and we end up with this deposited or hardened material, which may be something similar to the sintered or melted material which we encountered in PBF. Say this is one layer. For the next layer, I again place another layer of photoresist. If I want to build cubes, I expose this very region. For the second layer, using my UV source and build up layer number two. This was layer number one. Similarly for the next layer, and so on and so forth. So is optical lithography an additive process? Would someone like to answer this? One thing which I did not mention purposefully is what happens after this UV exposure. What is this development phase? Once the photoresist is exposed to a UV source using a mask, the remaining material, so the material which would have been here, is removed, and it is removed by chemical etching or chemical machining. Whereas the definition of additive manufacturing says does not typically involve a subtractive or a formative step. Thus, in the true sense, it is not an additive manufacturing process. Then one might ask, what about laminated object manufacturing or sheet lamination? It is counted as a hybrid process for this very same reason. It has both additive and subtractive steps involved. Investment casting, on the other hand, you start with a mold, you fill it with wax or any other precious metal, and end up with your desired part. There is no layer by layer uh, processing in this case. There's very elementarily we can discard it as not an AM process, it is a conventional process. The next question again uh, on strategies in additive manufacturing. What is a viable strategy to avoid support structures during additive manufacturing? Do we modify the design to correct overhangs? Well, typically your client gives you a rigid design. While some modifications must be made to adapt it to the additive process, If the design itself has overhangs in it, say for the water tank that we saw in one of the few slides, you cannot just eliminate it altogether, or you cannot end up building a column with the same cross-sectional area as the tank itself. That just does not work out. Small modifications, wherever necessary, are permitted in the purview of the additive process, but we cannot per se modify the design to a great extent simply to correct the overhangs. So this is not a viable strategy. Is it possible? Yes. Is it feasible or viable? No. We utilize a preferential orientation to minimize or altogether avoid support structures. Say in the case of something similar to the water tank that we had. Say if we are trying to print this funnel. If I place it like this in my geometric CAD model and print it, these regions will have overhangs. And what the software will end up suggesting to me is to have supports here. And the need for these supports is actually dictated by the angle of inclination. So say this is the vertical direction and this is the angle theta in this case. Now typically we will have some critical angle, say theta critical, such that if the angles are smaller than this theta critical or the overhangs are shallow, we will not need explicit support structures and the material will be able to support itself. However, if this angle is larger than this critical angle, uh, support structures will definitely be needed. And we'll be talking about this critical angle in the upcoming lectures. However, say I simply use a different configuration for printing the same part. So in this case, what I end up doing is I invert it. Now we see that supports are no longer required because if I were to visualize it as a step-by-step process, say in the first layer, I print this much, and this, and so on. In each case, I notice that the succeeding layer is well contained within the previous layer, and thus we don't really require explicit support structures. Thus, just by simply changing the orientation or orienting it preferentially, in this simple case, I have avoided the support structures altogether. In other cases, it might be possible to minimize the support structures. And today, the slicing softwares mostly come with inbuilt options to suggest the optimum orientation. So this is definitely a case, a valid option. Option C is to use a stronger material. Again, typically your client will prescribe what material is to be used. And even if you did have the freedom to choose your own material, the need for support structures, as we discussed, arises out of the geometry of the part. That is, whether the overhanging section is inclined at an angle that exceeds the critical angle for that material and that process or not. Whether you choose to make it out of a stronger material will not really influence the need for support structures. Say you were printing this funnel with polymer, and to avoid support structures, you decided to make it out of some super alloy, such as Inconel. You will still end up needing support structures. So this option is not true. Do we use a build platform with high degrees of freedom? Say you have a part which is like a manifold, so something like this. And you are printing it on your substrate. Now, typically, if we were to just print this on a machine with only with a stage of with only three degrees of freedom, so X, Y, and Z, typically we would be requiring support structures for to support these overhanging regions. But if we were to use a stage with say more number of degrees of freedom, say 5 axes, such as a 5 axis CNC bed, what we can do is in each step we can tilt this manifold. Say if I am printing this plane at the time, I can tilt my bed such that the layer that I am printing is always, say, aligned with gravity. It's always perpendicular to gravity, and thus there is no need for support structures. So as I continue to build along different planes, I will keep modifying or tilting my stage, keep modifying the position of my stage, and thus I will simply eliminate the need for any support structures. Thus option D is also correct, and in this case we have options B and D. In which of the following scenarios would AM be preferable over conventional manufacturing processes? In case of low volume and high customization, yes, customization is easier to achieve via an AM route compared to a conventional one. High volume, low customization production. If the customization is low and the build volumes are high, that is you want to print, that is you want to manufacture a large number of parts, you would typically aim for a conventional process. For complex shapes and lattice structures, often AM is the only way to go. Low production cost requirement. Now, AM is typically not cheap, but they will talk about the capital investment in the machine, the energy sources, the power consumption, the skill that is required. AM typically is a high cost affair. So, for low production costs, it will not be suited. Thus, A and C are right options. Here we are asked to list out some of the possible disadvantages or drawbacks of the additive manufacturing process. I would trust that in the course of this session, I have given you enough insight to maybe come up with a few of them on your own. So I'll leave this as an exercise. Please think about it, and we'll maybe discuss in the next section, in the next lecture, as to what some possible disadvantages or limitations of the AM process may be. Let us now move on to the subjective exercises. The first being to find the equation of the plane in vector form that contains the following points: 1, 2, 0, 1, 4, 2, and minus 4, 2, minus 2. Now, similar examples were also covered in the class, so we are well aware that in such cases, the first step is to check for collinearity. That is, whether these 3 points lie on the same line or not. If they do, then there are an infinitely many number of solutions for the plane equation of the plane that may satisfy these 3 points. And the way to check for collinearity is, of course, yeah, we have space, is of course to check for the determinant of these 3 points. If the determinant is 0, the points are collinear. So let us do this. 1, 2, 0, 1, 4, 2, minus 4, 2, and minus 2. Let us compute its determinant. So I am just expanding along the first row. We have 4 into minus 2 minus 2 into 2 minus 2 into 1 into minus 2 minus 4 into 2 plus 0 times 1 into 2 minus minus 4 into 4, which comes out to be minus 8 minus 4 minus 2 into minus 2 plus 8 plus 0, which is minus 12. This is minus 2 plus 6 plus 8 is 6 minus 12, so minus 12, which is minus 24, which is clearly not equal to 0. So the points are not collinear. And we will have a unique solution for the equation of the plane. It contains these 3 points. And if we recollect from our lectures, the vector equation for such a plane can be obtained as follows. X1, Y1, and Z1 are the three coordinates of point 1. X2, Y2, Z2, and X3, Y3, Z3 are the coordinates for points 2 and 3. We can obtain an equation of the plane as follows: x minus x1, x minus x2, x minus x3, x2 minus x1, x2 minus, sorry, x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1. The determinant of this is equal to 0. So identifying our points as 1, 2, and 3. Let us compute this. The first point is 1, 2, 0, x minus 1, y minus 2, z minus 0, 1, 4, 2. So 1, 4, and 2. The third point is minus 4, 2, minus 2. Minus 4, 2, minus 2. The determinant of this is equal to 0. And let us set out to compute this. Again, expanding along the first row, you are free to expand along any other. X minus 1 times 4 minus 2 is 2 into minus 2 minus 0 into 2 minus y minus 2 0 into minus 2 minus 5 into 2 plus z minus 0, so z times 0 into 0 minus minus 5 into 2 equals 0, or x minus 1 times minus 4 minus 0 is minus 4 minus y minus 2 times 10 plus z times 10 is equal to 0, or minus 4x plus 4 minus 10y plus 20 plus 10z is 0, or 4x plus 10y minus 10z minus 24 is equal to 0. This is the required equation of the plane which contains all 3 points. We have a question on tessellation. Which properties of triangles make them a suitable choice for tessellation? So this was covered in great detail by Professor Kapil. Any three non-collinear points form a unique plane. Yes, any surface can be broken down into triangles. True. Triangles can only be further broken down into other triangles. So all of the above options are true. And I did some research into tessellation, and the question which might also have arisen in your mind, which is that is it possible to tessellate a surface with any shape? And turns out it is not. With triangles that are polygons with three sides, all triangles tessellate, and with quadrilaterals or polygons with four sides, the sum of angles contained within them is 360, and all quadrilaterals tessellate, meaning that they can cover a surface so that there are no gaps between them. Of course, they might not be the most efficient means, and they might not be able to cover all surfaces with high curvatures. For pentagons or five-sided polygons, there is a list of 15 types of convex pentagons which tessellate, but it is not rigorously known if this list is complete or there are other types of pentagons which may tessellate. Hexagons or six-sided quadrilaterals do tessellate sometimes, and there is a list of three types of convex hexagons which tessellate, and in this case it is known that only these three types may tessellate and there are no more. For polygons with sides 7 or more, there are no convex like polygons which tessellate. So, piece of interesting trivia. We are almost out of time, but we'll cover at least one more question. So, the next question is dealing with the unit vectors of the triangular facets. So, a few lines of a triangle from the code of an ASCII format of STL file are given. We have to find out the unit vector in the direction of the facet normal of this triangle. So let us just draw a schematic triangle here. Say this is our triangle, and let's name the points A, B, and C, of course, going in a counterclockwise fashion. And let the vertex A have the coordinates 1, 2, and 0. Let B have 1, 4, and 2. And let C have the coordinates -4, 2, and -2. Now, utilizing the information of these vertices, we are asked to find the unit vector in the direction of the facet normal of this triangle. And as I had mentioned while we were recapitulating the lecture contents, we can use the vector cross product to actually find this unit normal. So first, let us find the cross product of any two vectors. So here we can construct three vectors being AB, BC, or CA. So if I write the vector AB, it will be the difference of the position vectors of B and position vector A. So basically difference of the components, which will be 0 I hat plus 2 j hat plus 2 k hat. Similarly, if I write the vector BC, it will be -4 2 -2 minus 1 4 2 is equal to -5 I hat minus 2 j hat minus 4 k hat. Now let us compute the vector cross product of these two vectors AB and BC. So AB cross BC, and just a quick recollection of the steps to find the vector cross product. So we calculate the determinant of ijk and the components of the two vectors 0 to 2 -5 -2 -4. And if we expand along the first row, I hat times minus 8, 2 into minus 4, minus 2 into 2, so plus 4, minus j hat times 0 into minus 4, minus 5 into 2, so plus 10, plus k hat times 0 into minus 2, minus minus 5 into 2, so plus 10 again. This gives us minus 4 I hat minus 10 j hat plus 10 k hat. This vector cross product is a normal vector to both AB and BC, but it is not the unit normal vector. To find the unit normal vector, we have to divide the vector cross product AB cross BC by its norm or magnitude. So the norm in this case is equal to under root minus 4 square plus minus 10 square plus 10 square, which is 100, 200, 216. Thus, our unit normal vector is nothing but the cross product minus 4 I hat minus 10 j hat plus 10 k hat divided by the norm, which is under root 216. It might be possible to simplify this further, but for all practical purposes, this is the unit normal vector along the facet normal of this triangle. Perhaps the last question for today. Which file format are concerning file formats in AM? So what pieces of information are not contained in an STL file? We looked at how the STL file only contains information about the geometry or the geometrical representation. It does not contain any information about the topology, as was already listed out. And we also looked at the makeup of the STL files in both the ASCII format and the binary format. And there we saw that there was no information regarding the color or the texture or even any scope for storing information about the material. So none of this information are contained. The question asks us which pieces of information are not contained. So all of the options are correct. While STL continues to be the most popular and perhaps the most widely adopted file format for additive manufacturing applications, there are new formats that have come up which seek to actually fill in some of these gaps or address some of these drawbacks of the STL file format. Two such formats are given here. One is OBJ, which encodes the surface geometry of a 3D model. It can also store the color and the texture information, either in the form of a companion PNG file containing a texture map or a material template library containing face attributes. A second format is the AMF format, which is in fact the additive manufacturing format, an XML based format for communicating AM model data, including a description of the 3D surface geometry with native support for color, materials, lattices, textures, and constellations. Similar to STL, the surface geometry is represented by a triangular mesh, but in the case of the AMF file format, the triangles can also be curved. So you can have a very accurate representation of the curved surfaces utilizing this file format. We also had a couple of questions on the deviation tolerance and the angle tolerance, but we'll be taking them up in the next session. So I will stop here for now. I'm sorry we have run out of time. So in case you have any questions, you can pose them in the next session, which will be happening next Tuesday. And I hope that all of you join in and see you soon. Thanks for tuning in.